Hi everyone. Okay, we'll start in a minute. Just a second, please. Okay, could someone tell me what we were discussing yesterday? Yes, we. Does anyone remember what we were discussing yesterday?
Hello, sir. Good morning.
Yes, good morning.
Sir, I do have one question.
Yeah.
I was in different batch, sir.
Mhm.
So, have you ever started with we have started with any projects or
No, no, no. We are currently working on boosting algorithms, I believe.
no, sir? I just got I received a mail from Govi
Mhm.
regarding that project details, sir.
Okay.
So, I'm just making it sure, sir. It is
No,
from
no,
our
no.
batch or it is from
No, no,
prior
no
batch.
projects have started as of now.
Okay, okay. Thank you.
All right. Anyone who remembers, what was the last topic that we had covered? Yes, please. Anyone who remembers? Okay, let me check. Just a second. Okay, you're doing ensemble learning, and I just want to see, okay, what was the last thing that we had done? So I had like 4 sessions yesterday, so I'm kind of confused. Just a minute. All right, so we did up to random forests. Okay, got it. Okay, in that case, I'll start. Just a moment, please. So we have to discuss some theory first, and then we'll see the implementation of boosting algorithms. Okay. All right, so today we are going to see boosting. Give me a second. I just want to ensure that, okay, let me make myself the co-host here. All right. So in case you want to type anything, I mean, if you prefer writing, write to this mentor account. Yeah, I have 2 devices running and I'll be able to see your messages, and then you can, I mean, whenever you're having any concern or a query, just write to me and I'll respond immediately. All right. So yesterday we saw bagging in the context of random forests. Okay. Today we are going to see this one more concept called as boosting. And before I start with this boosting concept, we need to understand what is the main difference between the two. Okay. Both are ensemble learning techniques. That's the first thing you need to know. So you use multiple models, combine their predictions to get a improved estimate of, you can say, your results. So let's have a quick recap of what bagging did. So in random forest, we had multiple models, right? D1, D2, D3, and so on. Okay. Let's say we had P models. Okay. I have a question for everyone. Do you remember how the training sets are built for individual decision trees? What are the two things that we do to build the decision trees? Anyone? See, please interact that way. You'll have more takeaways.
First, we take like a percentage of the total number of samples
With replacement?
with replacement, and then over that particular set of samples, we do feature selection.
So these are two concepts, instance bagging and feature bagging, right? So instance bagging is selecting samples with the replacement, and feature bagging is basically selecting a subset of your features to build each tree. And we need to ensure that these decision trees are diverse. Okay. Now, once the training sets are built, let's say the training set for D1 is T1, D2 is T2, and so on. My question is this. Would you call these decision trees to be independent? I mean, if you are, say, constructing T1, do you think construction of T1 impacts T2?
Yes,
How?
because I'll try to take those features in T2 which are not in T1. So if
That is, but how is it that is impacting it? So you are going to select it randomly, right?
yes,
So does random selection kind of affect T1 and T2?
no, randomly it won't.
So aren't they independent of each other?
Yes,
That's the question. Okay. So the essential part is all of these decision trees that you're building. Okay. See, how can you say that something is truly independent? If you can do those tasks, I mean, on say different machines. So if I give you these training sets, can you build each of these decision trees separately? Is that possible? So if I give you these training sets, can you train these decision trees on separate machines? Yes or no? You can, right? That's the big issue. Okay. So these decision trees are independent. Okay. That's the first key thing to note. Okay. They are independent models. Okay. Each model is independent. Now, another thing to note is this. When you are building these decision trees, is there a constraint as such about the height of the decision tree? Like, do we limit the height of the decision tree? Did I mention anything like that? Okay, we are going to put any constraint on the height of the tree.
by setting the hyperparameters, yes.
You can set it, right? But there is no constraint as such, right? I mean, explicitly. Did I mention, okay, we will build it up to say one height only or two height only? No, right? So, I mean, is it possible that a fully grown tree can give you best results? It is possible, right? Okay. So you have to find out, you can say the best height. Okay. I'm not denying that. But there is no condition on the, you can say the growth of the tree. So each of the decision trees, you can say, see, obviously we want to have shorter trees because shorter trees tend to avoid overfitting. Okay. And longer trees, they are more prone to overfitting. That's the thing. But you have to check. You cannot always say that longer trees will always overfit. Okay. So if only when a longer tree overfits, then I will try to reduce its, you can say, reduce the structure of the tree or reduce the height of the tree or whatever pre-pruning or post-pruning heuristics you apply to it. So I will say that each of these independent models, they are shallow trees. Does that make sense? Like shallow trees are preferred, right? Okay. So it's not necessary that, okay, you will always have long trees, but I will say shallow trees are preferred. Shallow means up to a decent depth. It's not too big and it's not too small either. Okay. All right. Now we are going to see another concept called as boosting. So here also you build multiple trees. Okay. Here also you build multiple trees. But there is one big difference. The big difference is, so I will explain it with the help of an analogy. So imagine there is an exam, okay, and you are allowed to cheat in this exam. So when I say cheat, basically you can give this exam in groups. So let's say that there are two prominent groups. One group is hostlers group and the other group is day scholars group. Okay. Which group do you think will perform well in the exam and why? You can assume, okay, almost all the people in hostlers and day scholars, they have the same capacity or same capability.
Hostlers
Okay, why? Why?
will be together most of the time, so they can use.
Yeah, they have a lot of coordination in between
Correct,
them.
right? So the idea of boosting is the same. So what in boosting, what you do is, let's say D1 is going to study something, okay? So D1 is going to be trained on this data set T1. So can I say that whichever samples are in T1, D1 is going to train on it? D1 is likely to do better on the samples of T1, yes or no? See, when you are going to train a decision tree on a data set, at least on that data set, decision tree is likely to do well, right? If I fully grow it, what would be the accuracy of D1 on T1?
100%.
100%, right? If you are talking about classification, more likely, most likely it would be 100%. There are scenarios where it could be slightly less also. Maybe I'll give you that scenario as well. Okay. At the end of this, we will talk about, okay, when there might, or you have to come up with a possibility that even if you fully grow the tree, in that case, like some of the samples can get misclassified. Okay. But it is very, it will be very rare to happen. It will be very, very rare. Okay. But there are possibilities like that. We will talk about it. But in general, it is like 100% accuracy. Now, one thing to note is that if D1 is getting trained on T1, so whichever samples are there in T1, okay, you can say on those topics, D1 will do well. All right. Now, how T1 is constructed is it's the same way as you are doing it in bagging. So the construction of T1 is using, you can say, random sampling with replacement and a subset of features. All right. And there is one more thing. And the thing is that you will only build each model. So each decision tree is going to be built up to one level only. Each decision tree will be built up to one level only. The maximum depth is 1. It is fixed. Okay, this is fixed. This is also called as a decision stump. This is also called as a decision stump. Now, if you are going to grow the tree up to one level, what can you say? Is it going to be a strong model or a weak model?
Weak.
In general, it's going to be a very weak model, right? So people use a terminology called as a weak learner. Okay, people use a terminology called as a weak learner for this. So each decision tree that you will see will be a decision stump. Okay, the max depth would be 1. All right, keep that in mind. And I'm going to show you if you combine multiple weak learners, it can be even better than what you do in bagging. All right, it can be even better than a very strong decision tree. All right,
Sanatan, like what called weak learner? This one step decision tree called a weak learner, or
you can say, okay, let me define weak learner formally for you. Assume that you are doing binary classification. Okay. All right. So the output would be what?
0 or
0 or 1, right? Or -1 or 1.
Yeah.
Okay.
Either anyone. Yeah.
Either anyone, right? So let's say there is some output. Okay. Let's call it y1. So assume y1 is either 0 or 1. All right.
Okay.
So there are many outputs on which you want to predict, right? For which you want to check how good is your performance. So if I give you a test set, you will have the actual labels, right?
Yeah.
Okay. Let's say you have n samples in it. My question is this. What is the minimum acceptable accuracy for your model that you will accept? Okay, if this is the acceptable accuracy, I will take it, otherwise no. Minimum acceptable, I'm asking.
Minimum acceptable. In general, you're asking.
In general, yeah. Okay, let me define it like this. Assume that y1 is say 0. What is the chance that like Y1 will get correctly classified. Let's say you're doing something.
Okay.
What is the probability that Y1 will get correctly classified? Can you suggest me a simple experiment with the help of which, without even training a model, I can predict Y1?
Will be 0.5.
It will be 0.5, right? I can do a coin
Yeah,
toss
50-50,
basically.
yes.
Okay, I can do a coin toss. If it comes down to a head, I'll say it is 1, otherwise it's a 0. So there is
Yes.
a 50% accuracy of, Y1 being classified correctly. Does that make
Yes.
sense?
Yeah.
Okay. Similarly for Y2 and so on, for every sample, right?
Yeah.
So can I say that if I have a lot of samples, I'm going to expect at least 50% accuracy?
Yeah.
See, let's say if n is infinity, what would be my overall accuracy? Exactly 0.5, right?
Yeah.
If n is infinity, right? Because when you have a lot of samples, right, almost half of them will be correctly identified. Does that make sense?
Yeah.
So can I say that if I'm going to train a model, I expect at least 50% accuracy? Because otherwise I can use a coin toss, right, to do this.
Yeah. Yeah.
All right. So a weak learner is that model which does better than chance. The formal definition of a weak learner in the context of classification is a model which does better than chance. And what is the chance in this case? Chance means basically predicting it heuristically. Okay. 50%, doing a coin toss.
Coin toss. Okay.
Okay. So in this binary classification case, for the context of binary classification, a weak learner is something. See, it is a learner, right? So it is learning something. You can call it a weak student. Okay. But it's a student, it is learning something. So its accuracy has to be greater than 0.5. Does that make sense?
Yeah.
And can I say error has to be less than 0.5?
True.
True. And you can say something is a strong learner if its accuracy is like really, really high. Does that make sense? This is like the formal definition of a weak learner. Now the question is, if you grow a decision tree up to one level, all right, can I say that if you were at this root node and now you have split it into two parts, it is more likely to increase, the performance is more likely to increase, yes or no? Otherwise, you would not have split it, right?
Yeah.
Okay. Does that make sense? I mean, this is pretty simple, right? If you think about it.
Yes.
Okay. Otherwise, you would not have split the tree, right? Your entropy would have been reduced if you are creating the children. If it was not reduced, you would not have split it.
Yes.
Okay. So I'm saying that you are going to grow the tree up to just one level, but one level is not going to give you a huge boost in the accuracy, right?
Yeah. Only
So-
0.5.
So the idea is you have very, you can say shallow, it's like the shallowest model that you can have. Okay, up to one level only.
Okay.
And I'm going to show you the power of these weak learners is actually when you combine them, you get the best model which can be possible. One of the best models which can be possible. It may seem very strange to you right now, but just wait for a while. Okay, just wait
Okay.
for a while. All right. All right. So now how this D2 will be built. Okay. So let's say D2. So you are now thinking of hostlers. Okay. So can I say that if they sit together, okay, if these people are sitting together, can I say that if D2 was a person, maybe D2 can quiz D1 about like the topics that D1 has studied? Is it guaranteed that if you are going to build D1 up to just one level, D1 will do well on all the topics of T1?
No.
No.
No, right? So, but it will certainly do on some topics of T1, right? Yes or no?
Yeah. Suddenly sometimes.
Okay,
Yeah.
on some topics of T1, and it might do it might do well on some other topics which are even beyond T1. Yes or no? See, if you are learning something, okay, if you are learning something, you also generalize, right?
Yes.
So can I say that you will do better on some of the topics which are even beyond T1, right?
Yes.
Yes.
Okay. All right. And you might do worse on some of the topics which are beyond T1, right? But since you are learning on D1, can I say on the majority of the topics of D1, even if you are up to one level, you will do well? Not majority, let's say 60%, 70%. Does that make sense?
Yes.
See, you are still doing binary classification. If you don't even have a 50% accuracy, do you think you will make this decision tree?
No.
That is what the concept is, right? That is why I'm saying it has to be a weak learner. If you have an accuracy of greater than 0.5 by growing this tree for one depth, then you will accept it, otherwise no. This is a strict constraint, okay? This is a strict constraint. This is a strict constraint. This has to satisfy, all right? Otherwise, this boosting technique is not going to work, all right? So assume that D1 is a weak learner now. I hope you have realized the fact that it will do better on the topics of T1 and may do good on some of the topics which are beyond T1, all right? But will be worse on most of the topics that are beyond T1 and maybe worse on some of the topics which are in T1, all right? Now, what will D2 do? So if D2 is a person who's going to assist D1, can I say that D2 can quiz D1 on some of these topics?
Yeah.
Yes or no? So I can just, you can say D1 is going to read some of the topics from a book. All right. And then D2 can quiz on all the topics from that book. So D2 will realize on whichever topics D1 is not doing well. Yes or no?
Yeah.
And then D2 can focus more on those topics on which D1 doesn't do well.
Yes.
Yes.
Similarly, let's say what will D3 do? D3 will do well on those topics on which D2 doesn't do well,
Yeah.
and will focus less on those topics on which D2 is doing well,
Yes.
Yes.
and so on. So it's like a sequential process. It's not parallelizable. It's a sequential process where you can say the next person in line or the subsequent learner is going to assist the previous learner. Is that part understood?
Yes.
Yeah. Yeah.
Okay. So that is how boosting kind of overpowers bagging. All right. So the models are trying to assist each other in terms of fulfilling you can say in terms of fulfilling each other's mistakes, in terms of taking care of each other's inadequacies. Okay. So they try to assist each other, but only the subsequent learner helps. Okay. It's not that everybody is helping. Okay. So D2 assists D1. So you can say DI plus 1 is going to assist DI. Does that make sense?
Yes.
And the constraint is that they have to be a weak learner. If this doesn't satisfy, then you can say boosting will also not work. All right. So let's try to understand how we are going to train these decision tree models. Okay. All right. So I'm going to give you a small example just to illustrate everything, how this works. All right. But before I start this explanation, let me clarify a few things. So DI plus 1 is going to, okay, DI plus 1, you can say will focus more on the misclassified examples or misclassified samples by DI. Does that make sense?
Yes.
Yeah.
And DI plus 1 will focus less. When I say will focus more and less, it does not mean that, like when I say focus less, it does not mean that it will simply ignore them. Can you please mute yourself for a while?
Hello.
I'll mute this person. Who is this person, by the way? Can you tell me the name?
That is Rahavendra.
Raghavendra. Okay, I'll mute her. Okay, all right. Okay, so DI plus 1 will focus less on correctly classified examples. All right. See, when I say it will focus less on them, that doesn't mean that you will simply ignore them. Okay, think about this. When an exam comes, will you be basically, so will in this case, let's say, will you say that D2 will just focus only on those topics on which D1 is not doing well? It will study all the topics, right?
Yeah.
But kind of will emphasize more on those on which D1 is not doing well. Okay. And how can D2 focus more on those topics on which D1 is not doing well? Can I say that it can focus more on those topics if I can incorporate more of those examples in T2, right?
Yes.
See, I know whichever samples D1 is misclassifying. Okay. Can I say that all those samples which are getting misclassified by D1, if they have more chance in coming to T2, if they have more chance in coming to T2, do you agree that D2 will focus more on those examples?
Yes.
Yeah.
So the idea is it is probabilistic. Okay. I am saying that I will increase the probability of those samples which get misclassified by D1. So the probability of those samples which get misclassified by D1, it will be more for those and they can come to D2. Okay. Similarly, the probability of those samples which get correctly classified by D1, their probability is going to decrease. So they are less likely to be available in T2. Do you understand the logic behind this?
Yes.
The idea is very simple. So assume every sample has some probability. Okay. Or maybe I'll explain it with this example. Okay. Let's start building the first model D1. Okay. All right. Now, let's say we have 6 examples. I'm just taking a small synthetic data set to illustrate this. Imagine we have 6 examples. You have a bunch of features for these examples, and the outputs are, let's say, there are 3 zeros and 3 ones. See, I'm explaining it in context of binary right now. You can think in terms of multi-class also, it will still work. Yeah, it will still work. Okay. So how do we build D1? And how do we build T1? That's the first data set that we build, right? So it is built in the same way as that of a random forest. So you will do instance bagging and feature bagging. So out of the 6 samples, can you tell me how many do you want to select? Just give me a number.
3.
Okay. Let's take 4 because 3 is actually just half of it. Okay, 3 is very little out of 6. See, do you remember I spoke about this right in the beginning that let's say if you have 1,000 examples, and if I take just 500 examples from it, the decision tree is going to be, very weak, right? In the case of random forest.
Yes.
Okay. So if it is very weak, and what I do then is I do instance bagging, right? To ensure that I get more examples. So I can have this number exactly as 6 also, right?
Yeah.
But it will not touch all the examples because now you're doing it with replacement. Does that make sense?
Yes.
Okay. So you should increase this number as high as possible. So 3 is actually a very small number. Let's take this number as 4. Okay. Let's assume, okay, you can take 5, 6, whatever. You can even take 3. But with 3, my example will not work. Okay.
Okay.
The way I have constructed it, my example will not work. Okay. So I'm going with 4. Okay. Let's say we take this 4 examples. So we have 4 places to fill. Does that make sense? Okay. I'm going to take these 4 examples. I have 4 places to fill. The thing is, I have to do it with replacement. Please don't forget that. So imagine there is a bag where you have 6 samples, X1, X2, X3, X4, X5, X6. So you put your hand in the bag and you take out one of these samples. Okay. You are going to select this first sample. Okay. You are going to decide what sample should come in the first position. Can you tell me what is the probability that you will see X1 in the first position?
1/6.
1/6, right? Does that make sense to everyone? Every sample is equally likely, right? Yes or no? Every sample is equally likely. Is this part clear? I'm writing D1 here just to illustrate that this is for decision tree 1. Okay. What about the second position? Is it still the same?
Yes.
Right? It's the same, right? So every sample shares the same probability. Can I call it?
Yeah.
Yes.
Okay. So I'm going to define this term in some notation. Okay. I'm going to write it like this. alpha xi dj. Okay. This means that this is the probability of sample I, sample xi, all right, for decision tree j. Okay. So if I ask you what is x1 of d1, you just figured it out, right? What was this number?
1/6.
1/6. And it is the same for every, right? Everyone. Does this make sense?
Yeah.
This is the same for everyone. All right. Now, what we do is, okay, let's say we select these samples. Let's say this time x3 comes out here also, maybe say x4 comes out, x5 comes out, and maybe say x3 one more time comes out. Okay. This is a possibility, right?
Yeah.
Yes, sir. Okay. All right. So I have these 4 examples in my root node. Okay. In my root node. I'm going to construct my decision tree 1. Okay. Let's say we are going to use entropy to decide which feature will be selected. So currently, what is the entropy of this? So if you look at these 4 samples, you have 2 zeros and 2 ones. Yes or no? X3 is coming twice,
Yeah.
right? Do you see that?
Yeah, yeah.
So 2 zeros and x4 and x5, they are ones. So this is coming twice. And the other 2 are just coming once. So you have 2 zeros and 2 ones. What is the entropy?
0.5.
No, it's 1. See, when they are equal, you have the highest entropy, right?
Yes,
Okay.
uncertain.
That is the Gini that you are computing, right? Gini is 0.5. Okay, it's not, I'm talking about entropy. Now, if you do this, okay, what we have to do is we have to create children, right? How many options do I have for my features? How many options do I have for my features?
D.
Look at the data set, D features, right? So if you are going to use feature selection, basically feature bagging, all right, maybe I have, say, some features to look at. Let's just think that, okay, we are going to use all the features. So what I will do is I will select these features one by one. I will try to see which feature maximizes the information gain. And based on that, I will create the split, right? Yes or no?
Yes.
Okay. So let's assume that one feature, which is say some xj, is going to create this split, and you have certain threshold for this. Okay. We have discussed about these thresholds in detail. So based on what the threshold is, some samples will go to the right and some samples will go to the left, right? Yes or no? That is possible, right?
Yeah,
Okay.
yeah.
Let's say that this x3 goes to the right. So both x3 will go to the right, right? It is not possible that one x3 goes to the left and one x3 goes to the right.
Yes.
Does that make sense?
Yeah.
So both x3 go to the right, and maybe say x4 goes here and x5 goes here. Okay. So if you look at the situation, there are 2 zeros and 1 1. Okay. And here is just 1 ones. Yes or no? Does this make sense?
Yes.
All right. All right. Okay. So you have created this decision stump up to 1 level. I'm not going to go any further. This is where I'll stop. Okay. This is your decision stump ready. Yeah, this is your decision stump. All right. So use this decision stump and let's try to answer some of the questions. Okay. So I'm going to gauge how D1 performs. Okay. Let's start how D1 performs on this sample X1. Okay. So let's start to gauge this. So if you pass, so instead of passing, talking about X1, let's start with maybe the sample X3. So if you pass this sample X3 to it, can you tell me where will it exactly go? Will it go to the right or the left?
Right.
Right only, right? Because both the X3s are falling on the right. And if you end up in this leaf node, can you tell me what would you predict?
0.
0 is the majority there, right?
Yes.
Okay. So is it correctly identified?
Yes.
It was actually 0. Can I say that X3 got correctly identified? Okay. Makes sense, right? Okay. What about, say, X5? What will X5 be identified as? It will be identified as 1, right? It will go to the left. And is it correctly identified?
Yeah.
Yes.
So X5 is also correctly identified. Okay. All right. What about X4?
go to the right
Incorrect.
side and incorrectly
It
identified.
will be incorrectly identified, right? Okay. So do you realize that now that if you build the tree up to one level, it is not guaranteed that it will do best on all the samples, but do you see that it still did 66.66% of the samples correctly?
Yes.
The unique
Yeah.
samples, I'm saying. It did 3 out of the 4 samples correctly, right? There were 2 X3s. Yes or no? So on the training set, it is still doing fairly well, right? If you look at the accuracy, it is currently 66.66% in terms of the unique samples. Yes or no?
Yeah.
Okay. Now, let's talk about the samples which are not a part of the data set. Okay. Let's start with X1. My question is, where will X1 go? So it depends on the features, right, of X1. So let's say there is this feature XJ here somewhere, and this value is maybe say AJ. So can you tell me if you go, if AJ is greater than the threshold, where will this go?
X5,
No. If you look at this for sample X1,
left side,
okay, where will it go if AJ is greater than the threshold?
left side.
Left or right? If it is greater than the threshold. I'm
AJ.
saying AJ is greater than the threshold. Let's say threshold is 5 and AJ is 8. Where will you go?
So it will go to the left, right?
Right? No. Why will it go to the left? See, this is where the yes and this is where the no is.
Okay. Yes.
Okay.
And
Typically, that's what we do, right? If it is satisfied, we go to the right. Otherwise, we go to the left. Does that make sense now?
yes. No.
Yes.
Okay. So if 8 is greater than 5, you go to the right. Okay. What do you predict for X1?
0.
0, right? So it is correctly identified.
Yeah.
Okay. It depends on what the value is, right? So you can still identify if it is being correctly identified or not. Same thing for X2 and X6 I can do. I check out their values for the feature XJ, and then I can decide whether to go to the left or the right, and I can see which is correctly identified, which one is not. Okay. So let's assume that, okay, maybe say X6 didn't get correctly identified, but X2 did. Is it okay to make such a valid assumption?
Yes.
Okay, it looks valid, right? Okay, all right. Now, if I ask you, okay, what is your accuracy right now? What would you say on the entire data set?
4 out of 6.
4 out of 6, right? Is it greater than 0.5?
Yes.
Yes.
When I say it's a weak learner,
The accuracy
No.
was more than.
why not?
Accuracy.
Accuracy has to be more, at least 50%, right? Isn't it at least 50%?
Yes.
Yeah.
So it is a weak learner, right? Why not? It's not. Why not? It's a weak learner. I mean, accuracy has to be greater than 0.5, right? It is greater than 0.5. What about the error? Error is 2/6. It's less than 0.5. So it is still a weak learner, right? I mean, you can think of the reverse. Okay. Please note this. I'm going to make use of it later. Okay. I'm going to make use of this later. This is important. All right. Now, think about this. So you are not doing well on these samples X4 and X6. Okay. Let's take a step back and try to re-understand this term, these alphas. Okay. My question is this. If 1/6 was the probability for sample X1 to come in T1, right? Yes or no?
Yeah.
This was for the first position in T1. My question is this. If you are now going to construct D2, should this probability go down or go up? Knowing that X1 was correctly identified by D1.
Correctly identified.
Okay, let's talk about X4. Maybe this will give you a more intuition. So what do you think D2 should focus more on?
X4.
X4 and X6, right? These two
Yeah.
samples.
Yeah.
Okay.
Yeah.
So if you want these samples to come in the data set, should the probability increase or decrease? You want them to come in the data set for T2. Because T2, if they are coming in T2, then they will be focused by D2, right?
Yeah.
So what do you want to happen? Should these probabilities alpha X4 of this decision tree 1, which is by the way 1/6 right now,
Yeah.
do you want it to increase or do you want it to decrease? Currently it is 1/6. So it has equal chance with respect to every sample. Now you want it to be focused more upon by D2. So do you want it to increase or decrease?
Increase.
Increase, right? And what about samples which were correctly identified?
Decrease.
Decrease.
Decrease. And that is the idea behind these boosting. Okay, as simple as that. Okay, let me show you how the probabilities are increased or decreased. Okay, look at this. This is a formula which people who proposed this kind of boosting, they came up with. So alpha I of j plus 1, or I will write it like this. Alpha xi of decision tree j plus 1 is equal to alpha xi of decision tree j. So this is the previous probability. Okay. And this is the new probability. You can think of it like gradient descent. You can think of it like gradient descent. Okay. Now the question is, for the next decision tree, I'm going to multiply this with a quantity. So if xi is correctly identified, what should be this quantity?
Less.
Less than what?
Less than 0.5.
Less than 1.
Okay.
See, this is the previous probability, right? So previous probability for every sample is 1 by 6.
Yeah.
Okay. If you multiply this number with a number which is greater than 1, so the probability increases, right?
Increases. Yes.
Okay. But you want it to decrease if xi is correctly identified. So quantity should be less than 1, right? Okay. And what about the other case?
It should be greater than 1.
Should be greater than 1. Okay. So if xi is incorrectly identified, okay, or you can say misclassified, okay, it should be less than 1, or it should be greater than 1, my bad. Okay, quantity should be greater than 1. All right, it should stay at least the same or should be greater than 1. Okay,
Yeah.
all right, let's see this. So I'm going to define this quantity. Okay, please take a look at this carefully. So the researchers who proposed this, right, they came up with several quantities. Okay, and the quantity that I'm telling you right now is the final product, is the final formula that they after doing experiments, they realize, okay, this is the one which is working the best. Okay, so the quantity is given as e to the power of plus minus 1 by c ln of 1 minus error of decision tree j by error of dj. Okay, I'll explain everything. Okay, just wait for a while. C is a constant. Okay, it's a constant, which is a positive constant, so it's greater than 0. Okay. So positive constant is greater than 0. Can I assume C to be 1 for now?
Yes.
Yeah.
Okay, let's assume C to be 1, but you can assume it to be anything. Okay. All right. Now, one more thing. This plus sign is for when xi is misclassified. And minus sign is for when xi is correctly identified.
Correctly identified.
Okay. You will see that this quantity will be greater than 1 if your xi is incorrectly identified, and this quantity would be less than 1 if xi is correctly identified. Okay, let's see how. Okay, now let me try to solve this if c is equal to 1. Can I say this will be coming out like this? Yes or no?
Yeah.
What can you say about the error of any model? What can you say about the error of any model? If it's a weak learner?
50%.
No, at least less than
At
50%.
least. Yeah. Less than 0.5.
Error of any decision tree J has to be less than 0.5, right?
Yeah.
Okay. You can see that in your D1, what was the error? 2 by 6, right?
Yeah.
It was less than 0.5. This is important. That's why I said this has to satisfy. Okay. So if error is less than 0.5, can you tell me will the numerator be greater than, the denominator, or the denominator will be greater than the numerator?
Numerator will be greater.
So if numerator is greater, can I say that this quantity will come out to be greater than or equal to 1?
Yes.
And don't you think we want it?
Hmm.
Look at this, when xi is misclassified, I use the symbol plus right here.
Yes.
Okay, I use the symbol plus here. Do you see that it comes down to be greater than or equal to 1?
Yes.
Okay, let's see if the symbol is -1. Okay. Okay. See, do you guys know that if I am doing, say, log of any number and the power is a, I can write this as a of ln of b.
Yes.
Okay. So I can take this -1 in the power, right? And e to the power of ln is simply just 1. So basically the power comes out and this is to the power -1. So this is like ej by 1 minus ej. Do you realize that this will come out to be less than 1?
Yes.
Okay, let's say less than 1, equal to 1, because it depends on if, see, ej is going to be, always less than 0.5, right?
Yes.
It will always be less than 0.5. So this quantity will be less than 1 and this will be exactly greater than 1. Okay. All right, makes sense?
Yes.
Okay. So let's use this formula to update the probabilities. All right. Can I directly do this without any computations? What do you recommend?
Yes.
Okay, so let's say I computed this. So this will be 1 by 6 into, what is ej right now? 2 by 6. So 1 by 6 into, this value would be 2 by 6 divided by 4 by 6. So this would be 1 by 24, right? Yes or no? Sorry, 1 by 12. My bad. Does that make sense?
Yes.
Okay. So this comes down to be 1 by 12. Because x1 was what? X1 was correctly identified. So you can see that the probability has reduced, right?
Yes.
It has gone down from 1 by 6 to 1 by 12. Let's do it for this sample 4, which was incorrectly identified. Okay. This was 1 by 6 originally. So 1 by 6 into 1 by 6 into 6 by 2. So this has become 1 by 3, right? Does that make sense?
Yes.
Okay. All right. So I'm just going to write the probabilities and let's see this now. Okay. So alpha of x1 for D2 has become 1 by 12. So this will only change for, basically x4 and x5. Was it x4 and x6 or what were the samples that were incorrectly
X4
identified?
and X6. Yeah.
X4 and x6, right? Okay. Does that make sense? It will be the same formula, right? So probabilities will not change. Okay. They will remain 1 by 12 for this. Now, is it guaranteed that, see, these are probabilities, right? Yes or no?
Yes.
These are probability scores. What is the sum of all probability scores in general?
1.
1. Do you see that currently it is equal to 1? Add them up. Do you see that it is equal to 1 currently?
Yes.
Okay.
Yes.
All right. If you sum it up, so 4 into 1 by 12 plus 2 into 1 by 3. Okay. So basically this is 3 into 1 by 3, which is equal to 1. Okay. So the sum is equal to 1. You can see that. All right. But the question is it guaranteed that after updating the probabilities, it will always be equal to 1? No,
No.
it is not guaranteed. So how do I ensure that these probability sum is equal to 1? What should I do? Can you modify these probabilities such that the score is equal to 1?
Divide them by the sum of all probabilities.
Divide them by the sum. So what is the current sum?
It will be sum will be 1 by 4
No,
into
what is the current sum? What is the current sum? You just did the sum, right?
1.
1. So it doesn't change anything, right?
Yes.
Yeah.
So if it was different, then sum will ensure that the final sum is equal to 1. Yes or no?
Yes.
So sum is nothing but the summation of all these probability scores. Okay. Does that make sense? Sum will be nothing but summation of all these probability scores, right?
Yes.
Okay. So just this is called as normalization. So this is an important step that you shouldn't forget. Okay. All right. In this procedure, there is this normalization step because it is not guaranteed that sum will always be very, very nicely summing up to 1. Okay. Now,
So if that was 1, in that case, like we'll summing up all the probabilities which are recalculated, and then we'll divide it.
yeah, no. So first you compute these values, right?
Yeah.
Okay. Then can you figure out their sum? First you compute
yeah.
these values and then you figure out their sum, right? Okay.
Yeah.
So the sum is like whatever probability sums that you computed just now, and divide by everything by the sum. Okay. So in this case, this is like 1 by 12 plus 1 by 12. All these values that you just computed. Okay.
Yeah.
In this case, it is 1 equal to 1. So it's not changing anything, right?
Yes.
If you divide anything by 1, it's not changing anything. And that's what we want, right? Okay. If the sum is different than 1, then you should divide it by sum, right? Yes or no? If it is any other value, okay, which is not equal to 1, then it will change the probability scores, right? These probability scores will change. Yes or no? The final probability scores will change.
Yeah.
Okay, that is what we want. Okay.
Okay.
All right.
So the probability should be always 1 when we were summing up all this. If
Yes,
not,
that should happen. Okay. If it is not the case, then you divide it by the sum.
sum. Okay.
Okay. All right. So now, can you see that the probability for x4 and x6 has increased and the others have decreased? Yes or no?
Yeah.
Okay. So now I have to repeat this experiment. So I have to construct T2. Okay. I have to construct T2. So I'll just make it on the same page. Okay. I have to construct T2 where I have to select how many samples?
Again 4 samples.
Again 4 samples. Okay. The process remains the same. You have to select again 4 samples. So you have a bag now, but you have 6 samples, but their probabilities are different. So how do you simulate this experiment now? Don't you think it became a little challenging?
Yes.
Okay. So there are many ways to do this experiment. Maybe I'll talk about one way, which is easier to understand. Okay. So my question is this. Let's look at the denominators, okay, of all these probabilities and compute the LCM. So what is the LCM right now? Well, multiply everything with the LCM. Okay, multiply everything with this LCM. Okay. So what is the value that you get for x1?
1.
1. So you have 1 copy of x1. How many copies of x2 do you get?
1.
1.
How many copies of x3?
1.
1.
For x4?
4.
4 copies. Okay. Do you realize where I'm going with this?
Yes.
Okay. Great. For x5 there is 1 and for x6
4.
4 copies. Now do you see that how many total number of samples do I have? It's actually 12, the LCM. Yes or no?
Yes.
You have now a total of 12 samples. But see, originally you had 6 samples, right? But you can now think of it as now you have a bag of 12 samples, 6 unique samples only, but some of them are duplicated more than once. Okay. Now, if you put your hand in the bag and select one sample, what is the probability for that?
1 by 12.
1 by 12 for any index, right? Yes or no?
Yes.
Yeah.
But the actual probability of x4 is what?
1 by 3.
12, 1 by
1 by 4. 3 by 4 by 12, which is 1 by 3, right? Okay. So let's say if I give you numbers starting from 1 to 12, if you select one of them, okay, you can fill this first place.
Yes.
So what is more likely to come? Think about it. The numbers which are repeated more, right?
4 or 6. Yes.
So, but is it guaranteed that 4 and 6 will always be repeated if you repeat this experiment more number of times?
No. No.
No.
Not always, right? But in general, x4 and x6 will come more, right?
Yes.
Yeah.
But so that is what the purpose was, right?
Yes.
Yes.
The purpose was to ensure that x4 and x6 should come more.
Yes.
Okay. So that's how now D2 is now focusing more on the samples which were misclassified by D1. And obviously, it will focus less on those samples whose frequency is less. And what are those samples that were correctly classified by D1?
Yes.
Does this make sense? So that's how
Yeah.
T2 is constructed. So in the same way, can you repeat this experiment over and over for every decision tree?
Yes.
You can, right? Okay. And finally, when you reach this pth decision tree, which is the last decision tree, okay, it is constructed in the same way, and whatever results that you get. When do you think this process stops? When do you think this process stops? So don't you think I can have a fixed number of trees and I will stop the process at the last decision tree? Yes or no? No matter what the situation is, I can go up to the end, right? So this is like depending on how many individuals I have in my hostel, right? Yes or no? I can continue this process over and over. And if they are all supposed to sit together, hopefully all of them combined will give me a good result.
Yes.
Yeah.
Does that make sense? Okay. All right. Now, but there is a catch. Okay. The catch is this. See, so D2 is focusing more on D1. Okay. D3 is focusing more on the misclassifications of D2. Okay. Is it possible if there is a hard sample, which because you're building the tree up to one level only, right? Yes or no?
Yeah.
So assume that if there is a very difficult sample to classify, then all of them will focus on that sample from D2 onwards.
Yes.
Yes.
Okay, does that make sense? Okay. So if there are difficult samples to classify, it is possible that because you are building these weak learners, none of the decision trees is able to do that well, right?
Yes.
What decision tree is likely to do well on it? Probably D1, right? Yes or no? Because D1 was built kind of independently, right?
Yes.
But all the subsequent models, they are actually taking care of each other's inadequacies. So I'm just giving you a scenario. Can I say that if there is a hard example which none of these decision trees is able to identify correctly, it will still remain incorrectly identified, but only probably D1 has correctly identified it?
Yes.
Yeah.
Yeah. I mean, I'm just saying, okay, in general, can I say D1 is like a universal model and others are kind of dependent on one another?
Yes.
And this kind of percolates as you go down the decision trees.
Yes.
Okay. So there is a good chance that all these models are going to basically have some of the samples which are being misclassified over and over. Yes or no? And despite having it, they are still unable to classify them correctly. Okay. So what happens is you are kind of trying to give importance to, I mean, the importance of such samples becomes higher and higher after every step. Okay. So that is what we don't want. Okay. So there are techniques which kind of, you can say if a particular sample is getting over and over, I mean, its probability is increasing, you would like to not increase it after a while, right? Because if it increases it too much, then every decision tree will focus on that only, right?
Yes.
Okay, so we don't want that to happen. Okay, so there are ways to handle such things. So if the probability blows up after each step, so you can actually curtail it down, and there are minimalistic measures for it. Okay. Another thing that I want to highlight is if somebody asks which decision tree should we rely the most upon, what would you say? What is the decision tree that you should rely the most upon? In general, I'm asking. Which decision tree gets to look at most of the samples? In general.
D1.
D1.
D1, right? And all others, then they focus more on inadequacies of each other, right? All right. So what happens is you actually reduce the importance of each of the trees by multiplying them with a factor. Okay, by multiplying them with a factor. Okay. So, and this factor kind of regulates how much the importance of each decision tree will be. So if L is 1, then everybody gets the same say, right? Yes or no? See, I have not multiplied this factor with the D1. Can you carefully see? I have not multiplied
Yeah.
factor with the D1. It's only with the subsequent modules. Okay. So if L is 1, then you are having equal say from each tree. Okay. But if L is less, can I say that the subsequent modules are not given enough weightage?
Yeah.
So L is typically a value which is greater than, you can say 0, but less than 1. Okay. So it's a value between 0 to 1. Okay. It is also called as the learning rate. Okay. It's also called as the learning rate. So this is very similar to gradient descent. So if L is small, you are taking small steps towards the minima, right? When you are doing gradient descent.
Yeah.
So here also L is kind of regulating how much importance is going to be given to each of the subsequent trees. All right. So if L is more, what can you say? Would I be done with small number of trees, or would I need more number of trees? If L is small, think about it. If you are giving very less importance to each of the subsequent trees, would you need more trees to get a more robust prediction, or would you need less trees? If L is small, think about it. If you have L to be very, very small, do you need more trees or less trees?
More trees, right?
More trees, right? Yeah, absolutely right. So the idea is like there is a trade-off between the two. See, okay, think about what are the hyperparameters of this model. One would be the number of trees, right? Just like the random forest model. Other is the learning rate. And these two are kind of, you can say, the inverse of each other. So if you have lesser learning rate, you need more trees. If you have high learning rate, you need less trees. But do you think I can give you the best value without checking?
No.
No, right? That is why we search on we compute the performance on the test sets, right? So you have to find the sweet spot between the two. Okay. So one idea is if you are looking for a lesser learning rate, okay, then try to have more trees. This is like a generic way to say it. If you have a higher learning rate, even a small number of estimators, small number of trees can give you a good result. I'm not saying the best. For the best, you have to find the sweet spot between the two. Okay. So I've just explained the difference between, like the trade-off between the two. Okay. There is a trade-off involved. They are inversely proportional to each other. Okay. One more thing. Now, if you have multiple people, okay, let's go back to this random forest. So if I have multiple decision trees and you are doing binary classification, how would you aggregate the predictions? How would you finally decide whether the output is 0 or 1? So every decision tree is going to say, okay, it's either a 0 or 1, right? So what do?
Predict proba and whatever.
No. It's okay. Let's say D1 predicts a 0, D2 predicts a 0, D3 predicts a 0. Okay. My question is this: how do you finally decide, okay, what label should be given, 0 or 1?
Majority.
Majority voting, right? Whatever the majority says in general. Is it guaranteed that each decision tree is going to be having similar performance?
No.
No, right? Okay. Especially in the case of boosting. See, in the case of random forest, can I say that it is somewhat likely that each decision tree will have similar performance?
Yes.
Random first, yes.
Assume that you have a very big data set and you are selecting, say, 90% of the examples from it. Can I say that most of the decision trees will share the same performance?
Yeah.
If you have a very big data set. For small data sets, no. But for big data set, it's kind of intuitive also, right? because you're going to select almost the same number of examples as that of your training set. Okay. So almost all the decision trees are likely to have the similar performance. Not all of them, but yes, most of them will have. But in boosting, is it likely to happen?
No.
What is D2 focusing more on?
Misclassifications of D1.
So it is focusing only more on those examples which are misclassified by D1, right? The previous learner.
Yes.
Is it focusing on all of them?
No.
I mean, there is some probability for all, right? If you think about it. But the probability for misclassified ones is more, right?
Yes.
Yeah.
In T2. So all these subsequent learners, they are not going to look at all the examples like from a wholesome perspective, right? So these decision trees are going to have, if I evaluate their accuracy on the entire set, what do you think? It will be like very, very different, or it will be like almost the same?
It will be different.
It will be different, okay? Because they are having their own examples to focus upon.
Yes.
Okay. So now that every decision tree has its own performance, but I can still get the accuracy from it, right? For each model. So
Yeah.
let's say decision tree 1 has accuracy 1, this has accuracy 2, this has accuracy 3. Each of the accuracies are different. Okay. How can I finally decide what is the result? Okay. Let's discuss this. Okay. How to aggregate the predictions. I think we did it last time also. Okay. So what does a decision tree predict actually? So I have a sample for which I want to make a prediction. So I give you this sample. Let's say the value is A1, A2 up to AD. So what you will do is you will give this sample to decision tree 1, right? So
Yes.
decision tree 1, it is going to end up in a leaf node. Okay. In one of the leaf nodes. There you will have some samples of class 0, some samples of class 1. So let's say you have some samples of class 0, some samples of class 1. You end up in a leaf node where you have 2 zeros and 1 ones. So what is the probability that your outcome is class 0?
Yeah.
2 by 3.
2 by 3, right? And the probability that it is class 1 is 1 by 3, right?
Yes.
And similarly, you can give it to D2. You will end up in a different leaf node. Okay. Maybe say you end up in a situation where you have say 3 zeros. Okay. And say 0 ones. So what is the probability for 0?
1.
1. And what is the probability for 1? It is a 0, right? Okay.
Yes.
My question is this: which decision tree should be given the most weightage? One with the highest accuracy or one with the lowest accuracy?
Highest.
Highest. Accuracy is directly proportional to your performance. Higher the better. Okay. Let's compute how much is the weightage in favor of class 0. Okay. Weightage in favor of class 0. So by D1, what is the weightage of D1? It's ACC1, right?
Yes.
AC1. Okay. And how much weightage, how much probability is given in favor of class 0?
2 by 3.
2 by 3. Okay. Is there any learning rate being applied to it? No, right?
No.
Not in D1. Okay. Let's think about D2. So its weightage is ACC2. What importance does it give?
1.
And what is the factor by which you are trying to reduce its performance?
Learning rate.
L. So can you do it for each and every decision tree? Yes or no?
Yeah.
So whatever this is, and you multiply this with L. Okay. This is in favor of class 0. Can you get in favor of class 1?
Yes.
The same way. What do you think we should predict, the higher or the lower one? Out of these two, so if I have weightage of class 1 as well,
Higher.
higher one, right? The maximum one. That is the answer. That's how you aggregate it.
Yes.
This is called as weighted predictions or weighted aggregation. Okay. Weighted by their individual performances. This is how boosting works. Okay. See, there are so many variants of boosting available in the market. Okay. In the literature, there is no limit to it. Probably there are more than 500. Okay. A lot of research has been done in this area. This particular variant is called as adaptive boosting. It adapts based on what samples the previous one was misclassifying. Okay, it's called as adaptive boosting, ADA boost for short. This was given by two people, Froon and Shapiro, in around, I think, 1995. And they got the Gödel Prize for this, which is like the highest prize that you get in computer science. And I hope, and I believe that like most of you were born before 1995, right? So this came out when you were alive. Okay. But most of the algorithms that you have seen prior, right, they came out much before, even before you were born. Okay. So this is the latest algorithm that you have, that you're looking at, that was developed after you were born. Okay. All right. Very nice algorithm. Okay. One of the best performing algorithms that is out there. So what it does is, so please note that, okay, let me ask you this. Do you think this algorithm is only made for decision trees?
No.
You generalize this process to say logistic regression because it also has probabilities, right? If you think about it. Instead of thinking about decision trees, can I use this with logistic regression? I will highly regularize it and will get a weak learner instead of a very strong learner. Yes or no? See, when I'm building this ADA boost with a decision tree, okay, I want to ensure that it's a weak learner, right? I am going up to just one level. How do I ensure that I get a very weak logistic regression model? I can do L2 regularization on it, right? With heavy penalty. And then repeat the same process. Who stops me? Nobody, right? So you can use this concept of boosting on any model as long as it supports the sample weights. Okay. As long as it supports this sample weighting mechanism. So almost all the models support sample weighting mechanisms except for this k nearest neighbors. So you can do this boosting with logistic regression. You can do it with obviously decision trees. Okay. You can do it with SVM, support vector machines, but not with KNN. Okay. Not with KNN. So. Okay. So these are some of the supported models. All right. Is this clear? You can even boost a random forest model, by the way. Okay. All right. The boosting is like a generic concept. All right. Any questions about this? Is it clear? Can you say a yes or no if it's clear?
Clear, Senate.
Thank you. Okay. Let's look at one more variant. Though there is only one variant in your syllabus, I think, okay, let me explain one more. Okay. That way you'll have more knowledge to take away. Okay. This is called as gradient boosting. Okay. I'm going to explain it. So please note that you can do boosting for regression also. So I'm going to explain this gradient boosting in terms of regression. This is the second variant that you're going to look at. Okay. You can actually use it for both classification as well. Okay. You can do it for both, but I'm going to explain it in context of regression. And same thing, the classification concept is the same. Give more importance to those samples, okay, which are misclassified by the previous learner. However, the way these updates are made, the formula is different. Okay, the formula is different. It is done using your gradients. Okay, that's why it is called as gradient boosting. So I'm going to explain how this gradient boosting works for regression and how it is different from this adaptive boosting. But let's see in the context of regression. That way you have both the flavors. Okay. So to understand this, let's take a small data set. Let's say we have some features and the outcome y. And the samples are denoted as like x1, x2 up to say xn. Okay. Now, since we are doing regression, what can you say about y? Since we are doing regression, what can you say about y?
Continuous values.
Continuous value. Okay, so y will be now continuous. Okay, or you can say real valued feature. Okay. Okay, so please note that it is not classification anymore. Okay, we are doing regression now. So when we were doing this classification, how did we know if a sample is correctly identified or incorrectly identified? What can we measure? What can we check? What can we check? Okay, if I give you a sample and if I ask you, say the prediction is 1, how will you know if it is correctly identified or say incorrectly identified? You look at its actual value, right?
Yes.
Okay, so you can compare the actual and the predicted values, and if they are equal, you say that okay, it is a match, otherwise it's a misclassification. Okay. Now think about this. If you are doing regression, how will you know that the prediction is like correct or not?
Take the difference between the prediction and the actual, and whatever is the difference, based on that we can say whether my prediction, if the difference is 0, then
Mhm.
my prediction is correct. Else, if it is not 0 but the value is very less,
Mhm.
maybe
Can I
0.0,
say they were like kind of correctly predicted?
yes.
Okay, all right. Does that make sense, right? Okay, all right. So, what do you think? Okay, do you think that if you create like these decision trees, okay, do you think for a real valued answer, will your predictions be the same as the actual values?
No.
Very, very rarely, right? But I can still measure the difference.
Yes.
And if the difference is very small, if the magnitude is very small, see, it could be negative or positive both, right?
Yes.
Your prediction can be, you can say, an underestimate or it could be an overestimate.
Yes.
Okay. So it depends on how you're measuring the difference, right? So it could be positive or negative. If it is
Yeah.
0, then you predicted it accurately. But if it is slightly negative or say slightly positive, then you still did a good job, right?
Yes.
But I still did some mistake. Does that make sense?
Yes.
Yeah.
It is still negative or positive. I still did that mistake. Okay, keep that in mind. All right. Let's see now how this works. Okay. So imagine that I am having this decision tree 1. Okay. Okay, I'm having this decision tree 1. Okay. Not even having this decision tree 1. Okay. I will build this decision tree 1 very, very soon. Okay. I'll show you how. Before that, let's imagine there is this node at which all the data is present. Okay. Let's assume that I'm going to take all the data. You can do instance sampling or you can say feature sampling, whatever you want. Okay. But for now, can I assume that I'm going to take all the data?
Mhm.
Will that be all right? Okay. Let's imagine I have taken my data set, which is say some training set, and I have these outputs here. So this is just one node, and these are the outputs of my training set samples. There can be some samples which can be missing. Okay, if you are doing instance sampling, there might be duplicates also. Yes or no? It is possible the way you pick this training set, right, from this huge data set. See, how do you build the training set for the first model typically? You do instance sampling, right?
Yes.
Here also you do instance sampling. Okay, so there can be duplicates. But for now, we are imagining that, okay, we have taken all the samples. So if you are just having one leaf node, okay, let's say one node only, what would you predict? This is just one node only. Okay, there is no splits, no children. What would you predict?
One leaf node.
Whatever is the value, why?
Okay, so, let's say I give you a sample, it will come to this leaf node, right? It will come to this root node. There is only one node. I can call it a leaf node also. Okay. So if I give it to this node, now the values are real. What do you predict? Okay, let's say these are the values 1, 2, and
The
3.
mean or whatever is.
Yeah, take the mean, right? You can take the mean of these 3 values, and that will be the prediction, right? Yes or no?
Yes.
So can I say that my prediction is the mean? Yes or no? So the prediction for every sample is the mean, right? If I pass all of these samples back again, For any sample that I pass back again, do you think the prediction will come out to be as y bar? Will it be anything else?
No.
No.
All right. Okay. All right. So how much mistake that you did? Can you tell me?
Y1 minus y bar plus it will be the variance.
So this is no. I am asking about the mistake. So let's talk about the mistake of the first sample. So mistake is also called as the residual. I'm measuring it as prediction minus actual. You can also measure it as actual minus prediction. Both would work. So how much is the residual?
So it will be y bar minus y1.
Does that make sense? This much is the mistake that I'm making, right?
Yes.
Okay. All right. Great. Okay. Now, so if I had only one tree, I have the output as y bar. Okay. Now, what is this guy D1 going to do? Okay. So think about this. If I predict y bar, can I say that I have a constant model?
Yes.
Okay. It predicts the same thing for every sample, right? Okay. Now, let's imagine this. I'm going to train this decision tree 1 in such a way such that I'm going to focus on the mistakes that was done by this constant model. So it's like we are doing the same thing as in, you can say, classification. In classification, what we did, the next learner held the previous model, right?
Yep.
By focusing more on those examples. Now what I'm saying is I will focus only on the residuals. Can I say that residuals are my mistakes?
Yeah.
So what I'm going to do now is this decision tree 1, you can even call it decision tree 2 if you want. Okay. If this was decision tree 1, now you're going to call something as decision tree 2. This will now focus on the residuals, on the mistakes. So you will take the same set of features and predict this residual by decision tree 1. And do you think that now, if I train a model which predicts the residual, the mistake of decision tree 1, I can use it for making the prediction for a new sample also? Yes or no? I can use it for making a prediction even for a new sample, right? So this is like, you can say, a mathematical model which predicts how much mistake the next model makes, okay, the previous model makes. Does that make sense? So ultimately what I'm saying is, forget these columns. Can you train a model by using these features and the output is this? Can you do that or not?
Yes.
Yeah.
So in simple English words, what is it? What is happening? Can I say that this new model is trying to predict the mistakes of the previous model?
Yes.
It's the same thing which happened in classification also, right?
Yeah.
But there were duplicates. Why there were duplicates? Because it was probabilistic in nature. Now the values are real. So it cannot be probabilistic, right? They were categorical values. These are real values. Okay. So my question is this: the second model that you see right now is going to focus on this particular output. Okay. So it is trying to predict the mistakes of decision tree 1. What do you think D3 will do?
Mistakes of T2 will be like taken care of in here.
Will be predicted.
But the rest of the residuals will be left over in D1 itself.
Yes. So, okay, let's think about this. Okay, how do you do the prediction then? Do you realize that now this will continue? So everybody is kind of taking care of the mistakes by each other.
Yeah.
Okay. So the last model is going to pick on the residuals of the previous model, right?
Yeah.
I have to stop somewhere, right? Ultimately. Okay.
Yeah.
Now the question is this: how do I make a prediction? And this is where the challenge is. Okay, this is where the challenge is. Let's see. Okay, so if I pass any test sample to the first model, what do you think this first model predicts?
The mean.
The mean, right?
Yeah.
What do you think the second model predicts? The mistake by decision tree 1. Yes or no?
Yes.
Yes.
Okay, let's call it y bar given by D1. Okay, this will be residual of decision tree 1, right? This will be the prediction. On that sample, how much this model thinks that the D1 made a mistake. Okay, what would be the next prediction? the residual of decision tree 2,
T2, yeah.
and so on. Can I say that the last one would be residual of decision tree P minus 1?
Yeah.
Okay. If I sum them up, don't you think that I get the prediction? See, basically, residual of decision tree 1 can be a positive or a negative value, right? It could be 0 as well. So if y bar was the actual prediction, what do you think residual of D1 would be?
0.
0, right? Hopefully. Okay. I'm not sure.
Perfect
Hopefully.
condition.
So if it was perfectly predicted, right, by this by this first model, then residual of D1 hopefully should be 0, right? Because there was no mistake. Okay. What should be the subsequent residuals? They should also be 0, right?
Yes.
Because there is no residual remaining. So you can say that, okay, as you are growing these trees, what will happen to these residual values overall? What do you think? They will increase or decrease? The magnitude. Let's talk about the magnitude. In general, what do you think the magnitude, what will happen to most of the magnitudes? Think about it. See, every time you're focusing on the mistakes of the previous model, right? Okay.
Yeah.
And you're looking at all the samples. This time you're not looking at a subset of the samples. So what do you think will happen to the residuals? Will their magnitude go up or will their magnitudes go down as you're growing more and more trees?
It should go down.
It will go down, right? Like in general, I'm saying it can
Yeah.
slightly go up for some of the samples, right?
So on an average, it will go down.
On an average, it will go down. Yes, absolutely right. Okay. Now the question comes, don't you think if it is always going down, you are more likely to overfit?
Perfect. Yeah.
Yes.
This is even more prone to overfitting. So what should we do? We should have a
Penalty.
learning rate.
Yeah. Okay.
In the same way, the previous thing that we had, right? Okay, learning rate kind of regulates the penalty. Okay, learning rate kind of regulates the penalty.
Penalty. Okay.
By the way, let me tell you, you can actually induce regularization losses that you have studied, like L2, L1. Okay, you can also include those. Okay, if you want. It depends on what model you are using. Okay, but please note one thing. This gradient boosting model is only applicable to decision trees. Many people actually tried implementing gradient boosting for other models. Okay, they tried implementing gradient boosting for, say, logistic regression, for naive Bayes. Many people tried for different models. Okay, but it wasn't very successful experimentally. Only with decision trees it came out and gave good results. Let me tell you, this came out in 2005. Okay, so it is even more recent than your adaptive boosting. And it is still the industry standard in most, you can say, handcrafted data sets. So when I say handcrafted, which means that you are manually selecting or manually extracting the features from raw data. Okay, so this is still the industry standard to this date. I will show you a lot of these packages which implement gradient boosting. Okay, though it is not there, I mean, in very detail in your syllabus, but I'll try to incorporate the state-of-the-art packages when we do the implementation probably tomorrow. So any questions about gradient boosting in general?
Santon, can you go to the next slide?
Yeah.
Yeah, I've asked about the D1, right? So when we were working on the D1, we'll calculate the residuals and then the residuals will be transferred to the D2, right? So
Yes.
that the correctly classified samples.
Classified. You shouldn't use the term classified.
Sorry.
Correctly predicted, you can say.
Okay,
Or
sorry.
you can say closely predicted instead
Yeah.
of.
So the closely predicted values will stays in the D1 and the incorrectly predicted values only go to the D2.
Oh, no. All the values are still there. Okay, all the values are still there.
Okay.
Even if it is 0, it is still there. But you know that the residual of those would be 0, right?
Okay.
But
So
it is there.
Okay. So the whole data set will be go to the D2 also, but based on the D1's data, what we have at residual and then the closely predicted values, the D2 will work, right?
D2 will be trained on that.
Okay.
But please note that there are a few things. See, instance bagging is still happening for each model. Feature sampling is also happening for each model. So it's not that every sample is being passed. You still know the residuals of all the samples, right?
Yeah.
So if I ask you to randomly select, so let's say there are n examples. If I ask you to select n samples with the replacement, don't you think you will miss some of the samples?
Yeah.
There will be duplicates, right? But you still know their residuals, right?
Yes.
So they can be zeros or non-zeros.
Yes.
So it is not that you are ignoring some of the samples. There in classification also, did you ignore any of the samples if you think about it?
No.
Probability associated with every sample, right? Even though
Yeah.
it may be low. Okay. So
Okay.
here also, it is like the experiments are still happening. You can say probabilistically because random sampling with replacement is still happening. Okay. But you are not increasing or decreasing the probabilities. Okay. Here the residuals play a role.
Okay.
Residuals will give me a kind of weightage. If the residual is very less, that means it is correctly identified by D1.
Perfect.
So it will, the weightage of that particular residual is very less in D2.
Okay, very spot on point. Okay, let me just give you a recap of what we did in decision trees. Okay, and why it is really useful. Okay, let's say you're making a regression tree, a single decision tree. Okay, so if this is your data and you're making a single decision tree, what is the condition or what is the criterion when you are creating these children? What should be the ideal characteristics for a child node? How do I do the splits in a regression tree such that these new child nodes are created? And what are the ideal or desirable properties about these child nodes?
It should be a pure node.
But now you're doing regression.
So I can take the sample value to
Think. We discussed this also, like when we talked about decision trees. What is the ideal property, okay, for these children? What do I desire? What do I minimize as I'm creating new children?
minimize the entropy
No,
maximum.
here the entropy and all those things, they are in classification. They are not in regression.
So you're asking how do I classify the children from the
Okay,
parent?
let's go back to classification. Okay, when I'm trying to create my children, what do I expect to happen in my child nodes? The purity should be high or low.
High.
Right now, I have real values in my root node. Okay, these values are real. How these values should be, you can say, partitioned. So maybe some values say go here, and some values maybe say, let's say go here. The remaining values go to the left-hand side. How do I want these values to be partitioned? What criterion is there? See, there it was the concept of purity, right? What is the concept in regression trees? We discussed this. Do I want these values to be far apart or do I want these values to be close by?
Far apart.
No, then you have forgotten what
Close.
the concept.
Yeah, forgotten the part.
Okay, see in classification, when I say all the values are pure, what does that mean? They are the same, right?
Yes.
Okay, so in regression, what do we want? These values to be
Closer, right?
Close.
okay. So which criterion do we use? Variance. You remember we talked about squared error, absolute error as well. I can measure how the values are far apart with respect to the variance, right? If the variance is zero, what will you say about this array whose variance is zero? All the values are the same. Yes or no?
Yes.
But now that you have real values, can I say that I can take their pairwise sum? I can take their pairwise absolute difference. I will still have an estimate of how close or how far they are, right?
Yes.
Okay. Now think about this. If you are going to train a model on the residuals, okay, imagine that these are the residuals. These y values, they are the residuals. So for all those samples whose residuals are, let's say, whose magnitude is very, very small, where do you think they will go? They will go in the same partition or they will go in a different partition?
Small residual, same partition.
Why? Because you want to minimize what? The variance, right? If they go in different partitions, what will happen? The variance of the children will become more.
Yeah.
Okay. So can I say that because intrinsically the way a regression tree is built, what it does is it tries to, you can say, cluster or group those points together whose values are close by.
Yes.
So if all the values, or let's say if most of the magnitudes are close by, don't you think they will be put in the same partition?
Yes.
Okay. Does that make sense?
Yes.
And if the values are very, very small, they will also put in the same partition. If you put them in different partitions, then your variance becomes more.
Yes.
That is not desirable. So you will not even construct that tree. So can I say that it will try to divide your data in such a way, such that leaf nodes in the first step itself, they will be having very low magnitudes. And this will have, hopefully it is going to create these partitions where the variance is minimized. Okay. But can I say that all those samples, let's say, who have a residual of 0, can they be put in the same partition? For all those i's which are zeros, don't you think I can directly put them in the same partition? Because the variance of all those would be what?
0.
If you have multiple zeros amongst these residuals, don't you think you can put them in the same in the same partition?
Yes.
You have got the least variance possible, right? And then you can think about, partitioning this data further. Yes or no?
Yes.
Right? So one more difference is there in adaptive boosting and this gradient boosting, that you are allowed to grow the tree to any level that you want. Okay, you can grow the tree beyond, to any depth. So this is not that you are just, having this up to one level. So in gradient boosting, you are allowed to grow the tree up to any depth, till the time basically you satisfy certain constraints. So here also, don't you think if you are using a decision tree, I can put pre-pruning and post-pruning characteristics?
Yes.
So you can decide on the max depth, you can decide on number of leaf nodes, you can decide on, say, minimum variance, you can decide on maybe say
Number of samples in a
number
node.
of min sample split, min samples leaf, that can also be done. Okay. You can think of putting a condition on, let's say, what should I say here? We have discussed 4, right? Min samples split, min samples leaf, max depth, number of leaf nodes. What else can we decide with this? Obviously, minimum variance is the 5th one. Okay. If you are using absolute error, you can decide on the minimum absolute error, like the minimum value for this, if you want to split it further. So these will be like your pre-pruning heuristics, and post-pruning you can think of just CCP alpha. Okay. So in gradient boosting, you are allowed to grow the trees to any depth. Okay. It's not that it's not similar to adaptive boosting, because you are now building a regression tree. So in regression tree, like you can grow this up to any level. Okay. So this would actually be your decision tree 2. Similarly, you will make decision tree 3 based on what residuals you get from this tree. And this process goes on continuing until you have built all the trees, or the residuals of the data that you have, they go to 0. Yes or no? See, imagine that if all the residuals are zeros for a tree, let's say you're building this tree, some DJ tree, and all the residuals are 0. Do you think there is a need to split the data?
No.
You will not even go any further. Okay, so this is where your process stops. Okay, this is where your process stops.
So I can say
Yes.
for each subsequent model, like for first model, my I'll fit it on data X and Y, where X will be n number of D number of features, and in for second,
No. The first model is just the leaf node. It's just one node, Y bar.
it's one node, but I'm asking about the data. Like it will be X, Y.
You can say it is XY, but there is just one node.
One node with X, Y, and then the second tree that I'll build
X and the residuals of
X and there one Y would change. It will now become the
these would change every time.
X remains same and Y changes every time, and Y will be the error made by the previous tree.
The previous model.
Okay.
Yes, that is spot on. Okay. And here also you have a concept of learning rate. How much weightage do you want to give to the subsequent models? Okay. So this decides, like if learning rate is small, you need more models. If learning rate is high, you need large models. Okay. So you have to find a sweet spot to get the best results. Okay. So you'll see the learning rate here as well. Okay. So this is your gradient boosting. I'm going to show you packages beyond sklearn also. when we implement this. All right. Any questions about boosting? Any questions about boosting?
No, Saturn.
Okay. All right. So these are the two variants. I think we have only 20 minutes left. So rather we will discuss a new concept and then we will do all the implementation tomorrow. Okay. But in 20 minutes, I cannot explain like boosting and like the two variants, and I'll show you the implementation for all the other models as well. That is not possible today. So we'll do that tomorrow. There is one more new concept that we should first discuss, and we will implement that also when we are implementing boosting. So this concept is called as imbalanced classification or skewed classification. So please note that we are now talking about classification only. But the name itself should tell you that there are some problems with it. Okay. So this is the scenario when we are having, I mean, you can have binary or multi-class, but one of the classes has a lot of samples and other class has very few. Does that make sense? So imagine we are doing, say, binary classification. Let's assume binary classification, okay, which is the simplest to imagine. So there are two classes. There are two classes. Let's say there are class 0 and class 1. So in the data set, maybe say you have 250 samples here and 750 samples here. So this is called as the minority class. I should actually do it the other way around. Okay, because typically 1 denotes the presence of something. Okay, so if you are looking at a medical data set, will the deceased patients be more or will the healthy patients be more?
Healthy more.
Healthy more, right? So 1 typically denotes the presence of a disease. Okay, so in most data sets you will see that. Okay, 1 is actually the, you can say, the minority class, which has fewer samples. Okay, relatively fewer samples. And this is called as the majority class. Now, I have a question. You also know that I think 1 is called as the positive class. It shows the presence of something, and 0 is also called as a negative class. Right? We discussed this in the case of binary classification also, right? When we started this.
Yes.
You can call it positive label or negative class, okay? Or negative label. Okay. All right. Now, do you remember we have already discussed one strategy that can kind of avoid this. So when we are going to train a binary classifier, okay, what do we ideally expect in terms of the number of samples for each class?
It should be equal.
It should be equal, right? For a good discrimination. So when we are going to discriminate between two classes, the number of samples for each class should be almost equal, right? Okay, that is the preferred scenario. But in most of the data sets that we have seen, that's not the case, right? So the question is, we have seen one type of hyperparameter in almost every classifier that we have used or that we have implemented, that kind of, you can say, mitigates the impact of the samples in the data set. What hyperparameter is there?
Class weight.
Class weight. Okay. So this class weight hyperparameter, we have seen, right, in almost all the models that we have seen, almost all classification models. And how do we assign this class weight? It's a dictionary, right? I hope you remember. So which sample, okay, or which class should get the more weight?
Minority will get more weight.
Minority will get more weight, right? So let's say if you have a majority class, which is here class 0. So you can give class 0 the weight as maybe say 2. Sorry, let's say class 0 is given the weight as 0.5. This is the weight for class 0. Okay, and then you have this minority class, which is 1. Okay, and then you give the weight maybe say as twice, or maybe say 1.5 times, whatever the number that comes to your mind. Okay, This is the weight for the minority class. And this is how you specify, right? Yes or no?
Yes.
We have seen this as a hyperparameter in our previous scenarios as well. Okay. So this is one way to handle. Okay. One way to handle imbalance classification. Let's talk about some more complicated ways. Okay. The ways are not complicated, but they make more sense. Okay. So imagine this is the scenario. Class 0 is 250. Sorry, class 0 is 750 and 1 is 250. Okay, this is the distribution of the samples. All right. By the way, you should note that even if the data set is skewed, right, decision trees can handle it very, very well. Did I mention it before? Did I mention it while during the implementation?
No.
Maybe you can take note of it. Okay, so models like decision trees, okay, they can handle, okay, they can handle, they can, I mean, they can kind of give you good results even when the data set is highly skewed. Okay. Any reason why? Because they create a separate partition for it. Yes or no?
Yes.
Okay, even if you have, okay, but other models they suffer. Okay, other models they suffer. So you can say model like decision tree and its variants. Okay, we have seen variants like random forest and boosting, right? So they can work even when the data is highly skewed. Okay, but other models kind of suffer significantly. So see, ideally we want equal number of samples. Okay, ideally we want equal number of samples. So 0 is the 750, 1 is 250. Can you tell me what is it that you want to do? You want to reduce the majority class or you want to reduce the minority class?
Reduce the majority.
Okay. So one way is you reduce the majority class. Okay. So strategy 1 is you reduce the majority class. Okay. So if you reduce the majority class, so do you think that I can select out of 750, maybe I can select 250 examples and the minority examples can be kept as it is?
Yes.
Okay. So you can do random selection, a random sampling with replacement also if you want. Okay. If you are training multiple models, you can even do random sampling, but retain the 250 of the minority as it is. Does that make more sense?
Yes.
So when you are having these 750, right, out of this you do random sampling with replacement if you are training an ensemble model. Okay. But if you are building just one model, then you select random samples like out of 750 without replacement. Okay. If you are building a single model. Okay. So it depends on what kind of strategy you are using, with or without. So you will prefer with, okay, when you are building an ensemble model, and if you will prefer without when you are building a single model. Does that make sense?
Yes.
Okay. All right. This is called as undersampling. This is called as undersampling, where you reduce the majority class examples. Okay. You are undersampling the majority class. Okay. Can you think of the reverse? Can you think of the reverse?
Duplicating my minority classes.
Duplicating your minority classes. So you can think of this concept called as oversampling. So oversampling simply means that you are basically increasing the minority class samples by duplication. Okay. So what are we doing? We are doing random sampling with with replacement. Okay, don't forget that. This is essentially duplicating, right? So maybe let's say you now want to increase 250 to 750, and this is 750 is retained as it is. Okay. Does that make sense?
Yes.
All right. Now let's try to discuss the potential problems from this. So this oversampling is also called as random oversampling of examples. There's a special name for it called as rows. Undersampling doesn't have a special name. Okay. Now let's discuss the bottlenecks of each of the approaches. Okay, what do you think this undersampling suffers from?
Maybe missing out information.
Missing out, right? So information loss is a problem. Just write it on red. So limitation is your what we say is information loss, because you are reducing the majority class examples. Okay, so if you skip important examples, then the performance can deteriorate. So instead of reducing it to 250, then you think I can still make it as say 300 and then check the performance?
Yeah.
Yeah.
Make it as 300. Maybe you check it, keep at 350 and then check the performance.
Yes.
Okay. Does that make sense? So I can try for different values, right, of my sampling. You can try for 400 also. I mean, and then see, okay, which is giving you good results. Because if you keep on increasing this, after a while, you will see performance decrease, right?
Yes.
See, who knows like what sampling is good or what sampling is bad. It is dependent on the data set, right? So we have to check. Okay. So we will see for different sampling rates, what is the performance, and then we will decide that particular sampling, which gives us the best results. Is that part clear?
Yes.
Okay. Now, what do you think is the problem with oversampling?
Incorrect information.
No. You are just duplicating, right?
Duplicating, yeah.
So if you duplicate a lot of examples, see, you duplicated almost every example thrice here.
More weightage to
Weightage to this. So if what will happen? What will the model become? It will be overfitted to.
the minority class.
It will now try to focus more on class 1. So don't you think that it will predict mostly now? So if you give duplicates of class 1, what do you think will increase, precision or recall of class 1? Think about it.
Precision will increase.
Or the recall. Think about this. Okay, think about this. What is recall? Recall is from the data set, right?
Actuals, yes.
From the actual data set. Don't you think if you give each sample which is 1 3 times, don't you think your recall of 1 would actually increase, not the precision? Precision might go down.
Yes.
See, I agree with you. You are saying that there are a lot of ones that will be predicted, right? Because now you are going to favor 1. But it is quite possible that some of the zeros also get predicted as 1s. So that way precision will decline, right?
Yes.
Precision is from the predictions. So recall would increase. Yes or no?
Using the actual data for 1, so that is why my recall is increasing for 1.
Recall will increase and not precision. Okay. So you can actually favor, okay. I mean, this strategy favors class 1 examples more, because if you do too much duplicates, so you might become overfit to minority class. Okay. All right. So the question comes, instead of increasing it to 250, don't you think I can increase it to 500, maybe then 550, then 650? Yes or no?
Yes.
Yeah.
So we will see with different sampling rates what can be done. Okay. Now, don't you think we can combine both the strategies together?
Yes.
Okay, we will do that also. So reduce one of them and increase the other one. Okay. So we'll see this strategy also. You can call it, this is a strategy 3. And now I'm going to talk about the strategy which works the best, okay, which is strategy 4. This is called as SMOT. Okay, I'll just write the full form first. It's called a synthetic minority oversampling technique. For examples, okay. SMOT. Okay, let's see how the strategy is different. So, see, please look at the definition. I mean, the title for this. It's an oversampling technique. So, what will this do? It will increase what?
Increase the minority.
It will increase the minority. Okay, that's the first thing. Now, please note that it will increase the minority, but will create synthetic samples now. Okay, it will create synthetic samples now. They will not be simply duplicated. Okay, they will not be simply duplicated. So I'm going to show you a strategy where you can easily visualize how synthetic samples are being created. Okay, so let's see with a simple visualization. So imagine you have two features like this. You have two features like this. Okay, and you have some data. Let's say this is your data X. Okay, and you have a lot of these triangles. Which class do you think is the majority?
Triangle is the majority.
Triangles, right? Okay. Now let's see how this strategy works. So let's say if I were to just duplicate the examples, don't you think the visualization will not change?
Yes.
So if I increase these 6 examples, maybe to 50. So I will make it 50x. Do you think visualization changes?
No.
No, right? Okay. Now what you will see is I'm going to create some minority examples synthetically. Okay. So one idea is, so there are many ideas how you can generate it. So the simple idea, I'm going to explain the vanilla version of SMOT. Vanilla ice cream you eat, right? Yes or no?
Yeah.
Vanilla means no flavor. Okay. So this was the very first version that was, you can say, proposed in the literature. So what it says is that you only focus on minority examples. Okay. Focus only on minority examples. Forget the majority. Okay. And then you repeat some steps. Okay. So the first step is select one example at random. Okay. Select any minority example at random. So I'm going to select one of them at random. So let's select this particular example. Okay. Okay, I'm going to select this example. Now the next step is find the nearest neighbors. Okay. So step 2 is find the nearest neighbors. You will be finding the nearest neighbors. So how many nearest neighbors you want me to find?
3.
Okay, let's go with 3. Do you see that? Okay, these are the 3 nearest neighbors, maybe?
Yes.
Yeah.
Okay. So let's say these are 3 nearest neighbors. So the second step actually is select one of the nearest neighbors at random. Select one of the nearest neighbors at random. So what is the hyperparameter here?
Distance.
Number of neighbors. In implementation, you will see that it is called as k underscore neighbors. Okay. This is the number of neighbors that you select at random. Okay. All right. So maybe let's say we select one of the nearest neighbors. Which do you want me to select? There are 3. Shall we go with, say, this one? Okay. I'm going to select this one. Okay. So I will just highlighting this one got selected. Okay. One of the 3 nearest neighbors. And where do you think we should create a new synthetic sample?
In between.
In between. That's the right way to do it. So create one sample here. Okay. So this is like the newly generated sample. Newly generated sample. So you can say create a new point. Okay. In the middle of the selected nearest neighbor. Okay. With respect to the selected nearest neighbor. Yeah. Okay. And let's say I want to generate 100 points. So can I say that step 4 is repeat step 2 and 3, repeat steps 1, 2, and 3, repeat steps 1, 2, repeat steps, let's say repeat step 1 to step 3. If you want to create, okay, let's say if you want to create 100 examples, so can I say for creating n new examples? Yes or no? Do you think that I can repeat these 3 steps for creating any number of examples? Any questions here? Don't you think that I can actually generate as many points as I want? See, next time I can select this point also as my starting point, right? Yes or no? And then you look at 3 nearest neighbors. These are the 3 nearest neighbors. I select one of them at random. Maybe say I select this point at random. I create a X here. Yes or no?
Yeah.
So you can repeat this any number of times and you can generate as many points as you want. Okay. This is Smart. Okay. Vanilla version of Smart. Is this clear?
Yes.
Okay. All right. Great. Okay. What is the advantage of it? Do you think it suffers from the same problems as that of your normal oversampling? Will there be any bias here if you think about it? Are there any duplicates? Do you think the model will favor like any of the minority class examples more? No, right?
No.
Because there are essentially no duplicates which are there. Okay. Okay. Let's try to understand some more problems with this. I'll just need 2 more minutes. Let's try to understand some problems with this. Okay. One of the problems that I will say is this. Imagine there was an X here. Okay. And maybe say there is a, okay, let's say there is an X here. Do you think it makes sense to generate points with respect to this point?
No.
Because let's say if you look at the 3 nearest neighbors, these will be the 3 nearest neighbors, right?
Yes.
And let's say if one of them got selected, let's say this got selected, you will create a point here. What do you think this point will actually do? This will induce noise, right?
Yes.
Yeah.
So do you think we should generate points? We should generate synthetic points from those minority class examples, which are encapsulated by a lot of majority class examples.
No.
No, right? Okay, that's not an advisable thing to do.
Yeah.
So there are strategies. So just with respect to this, okay, there are strategies that, so you can say to avoid this, okay, to avoid this, people have proposed several strategies. So there are so many different variants of SMOT that try to overcome this. Okay, so variants of SMOT try to overcome this. See, here we focus on only on the minority class examples, right? In the minority version. Okay, let me ask you this. If you look at the nearest neighbors actually of this point, these are the 5 nearest neighbors, right?
Yes.
So if I include the majority class examples, and if I say that, okay, if the majority of the examples belong to the majority class, can I say that I should not generate new points from this?
Yes.
Okay. This is called as adaptive SMOT. Does that make sense?
From the triangles, we were creating an X.
No. I am saying that now. See, what is the second step? The second step is to identify the nearest neighbors, right?
Yes. Yes.
I am saying that when you are identifying the nearest neighbors, just check if the nearest neighbors are actually the majority class examples.
Okay.
If the nearest neighbors are majority class examples, I should not make a new point from that, right? If you
Yeah.
think about it, okay. So that way, I mean, you can avoid this issue, right? This is called as adaptive smart. Okay, I'll give you one more. Do you think that I can, so on the original data, I can actually make a line which separates the data like this? Yes or no?
Yeah.
Yes.
Okay. Now, I want you to think of this. If a point is, say, in this region, will this point be correctly classified or incorrectly classified?
Incorrectly.
Incorrectly classified.
Classified, right? But don't you think I should create more points for this?
Yes.
Okay. So it is incorrectly identified. Okay. And if you look at its nearest neighbors, so you have to consider majority as well. If you look at its nearest neighbors, maybe some x's are here also. Okay. If you look at its nearest neighbors, these are the 5 nearest neighbors, or say 3 or 4, whatever nearest neighbors that we are looking at. So if the majority of the nearest neighbors are x's, okay, and it is misclassified, don't you think we should create more points from it?
We should.
We should, right? Okay.
Yeah.
This is called as SVM smart.
Okay.
SVM smart. Okay. There are so many variants. I'll show you all the variants. Okay. I am not going to implement all of them. It's just a function call that you have to do. You can check it out in your free time. Okay.
In this case, I'll have to,
Yes.
in addition to the number of neighbors, I'll have to see how much is the distance from the separating line, and then I'll decide.
Yes. On the basis of that, you decide. See, it is also possible that you are on the correct side. So if you are on the correct side, do you think there is a need to generate more points from it?
No.
No, right? So that is why you are doing this classification as well. So it is like going one step further. Okay. But the idea of nearest neighbor still holds. Okay. Idea of nearest neighbor still holds. Okay. Let me give you one more example. Do you really think
Santin, before we moving on to that one, like this triangle thing you said, right? Can you please repeat it once?
which one for which part?
That the x whenever the x in the majority of site, like
This one?
Yeah.
See,
Yeah, that one.
what I'm saying is that, see, what is the first step? You identify the nearest neighbors, right?
Yeah.
In the vanilla version, I only focus on minority class examples. Okay.
Yes.
Let's not do that. Let's focus on everyone. So
Okay.
find the nearest neighbors. So if the nearest neighbors, if they all belong to triangles, do
Okay.
you think we should create more new examples from this X?
No.
No, right? So that is why you avoid that. This is called as adaptive smart.
Okay. Okay.
Okay, there's a version of it which is called as adaptive smart. If you are using a classifier to decide, and obviously using the concept of k nearest neighbors to decide, should we, create more examples from it, that is called as SVM smart. Okay. There are so many other variants. I'll give you maybe one more. Okay.
Mm.
So imagine that you try to group these points. Okay. So you will soon understand, or maybe soon study after this particular topic. There is this idea of grouping. Okay. So forget that these are x's and triangles. Okay. Maybe I'll show you like this. Okay. Let's say there is this data set. Okay. There is this data set. Okay. My question is this: I want you to find the groups in this data. Visually speaking, how many groups do you see?
3.
3 groups, right? These are the 3 groups. Now, let me ask you this. Within a group, if you see that the labels are pure, okay.
No.
Okay, which class is actually the minority class here? Triangles, right?
Yeah.
Okay. So I'm saying once you identify the groups, if you look at this particular group, there is a triangle here, right?
Yes.
What is the majority?
X.
X.
We should create new, new examples from this triangle.
No.
It will cause more noise, right?
Yeah.
Okay. This is called as k nearest neighbor smart. You will soon study, sorry, not k nearest neighbors, k means smart, my bad. This works on the idea of identifying groups. Okay. And if in a group you have, you can say a majority of the points belonging to majority class, you should not create more points from the minority class in that group. Okay. Does that make sense?
Yes.
And there are other variants of SMOT as well. You will see borderline SMOT. So, I mean, you can try, you will see SMOT ENC. So there are so many different variants. Just, I would say, try implementing them. It's not guaranteed that, okay, one variant of SMOT will give you the best results. But from my experience, I see adaptive and SVM SMOT give the best results on most data sets. Okay. So I will show you vanilla SMOT. I will show you the web page where you have all these variants of SMOT. Maybe I'll show you one implementation of a variant as well. Okay.
So,
But yes.
Smooth, Sanatan, if I have like overall, I have triangle as my minority class, for example. And in a group, I have equal triangles and X's. In that particular group, should I create or should I not create?
No, don't create.
Okay.
Again, there are, see, the concept of nearest neighbors is still there. Okay, concept of nearest neighbors is still there. Okay. See, within a group, there is a possibility. Let's say there is this big group. Okay, think about this. So there is a triangle here. Okay, there's a triangle, and there is a big group with there is a lot of X's. Like this. This is also possible, right?
Yes.
It's one group. Okay. Now, if you look at the nearest neighbors, let's say you're looking at 4 nearest neighbors at this point, or maybe 3 nearest neighbors at this point. Okay. Should I create one more triangle? Think about it. Should I create one more triangle? See, if you look at the 3 nearest neighbors, these are the 3 nearest neighbors, right? What is the majority of the triangles? I mean, what is the majority in the nearest neighbors? It is still triangles, right? So I can create more triangles here. Okay. So don't forget that you still have the concept of k nearest neighbors. Okay. Don't forget that. But you're first identifying the groups. Okay. And then within a group you check. Okay. Then within a group you check. And then within a group you check.
So even though if the triangles and X's are equal in the group, this will work. So if I'm looking at the
Yes.
k nearest neighbors.
On the basically the orientation of the points, right? See, there might be, let's say all the triangles are equal here. Okay, let's say all the triangles are equal here. Let's say triangles are also in majority.
Okay.
I can still, so if I ask you that, let's say there is a triangle here. Okay. Do you think I should create more points from this triangle? The one which I highlighted here.
No.
No, right? Because let's say if there are some triangles here, they will cause problems, right? Even though they are all in the same group.
Yes.
Okay. So you still have to use this concept of nearest neighbors. But first you identify the groups, and within a group, then you check. Don't you see that like once you identify the groups, you are not searching with respect to all the nearest neighbors? See, find the nearest neighbors, what is it that you will do? You will compare it with all possible examples in the data set, right? Don't you think that once you identify the groups, you have kind of limited your search?
Yes.
Then you are searching for the nearest neighbors within that group only, right? So it is kind of avoiding that compute bottleneck for you.
Okay.
Okay. See, if you want to find who is the closest to you, you search with respect to everybody, right?
Yeah.
You cannot say without computing the distance, okay, this is the closest to me. But all I'm saying is that to avoid that computation with respect to everyone, why don't you just first identify the groups and then only with respect to the groups you check. You don't worry about the others. Otherwise, it will be huge compute intensive, right? Think about it. Yes or no? Okay. So k-means SMOT is, you can say more, you can say effective, but don't you think it will be very, very similar to this adaptive SMOT? It is kind of saving you the computations, right?
Yes.
Okay. But again, to find the groups, you have to worry about that. Okay. So k-means also is, to identify groups, it takes a lot of time also. So it depends on, again, the size of the data. So maybe for a small data set, you directly use, say, adaptive SMOT. For a bigger data set, first you identify the groups and then use k-means SMOT. Okay. So all have their, you can say, pros and cons. That's why so many strategies are there, right? If the universal strategy, I would have gone with one. Okay. So there are so many variants of it. And obviously, there is no single way to identify this is the best strategy unless you test. Okay. Unless you test. So you create more examples, then see the performance on the test set, whether if it improved or not. Now, please note that you are creating synthetic examples only for the training set and not for the test set. Okay, because that would be bad. Okay, you're only creating it for the training set. Okay.
So for the smaller data sets, the adaptive mode will be more adequate to use. And if it is the data set was very big, we'll use the grouping technology.
Yeah, k-means mode.
Okay, k-means.
K-means is the algorithm which is used to do grouping.
Okay.
So there is a request from Niveta. She says that can we create a WhatsApp group? Niveta, I would not prefer it. This is from my perspective. I will, from my side, it's a no. Okay, I cannot do this. Okay.
Sorry, sir.
No, I understand, Niveta. I understand your concerns. Okay, you are asking me to do extra stuff. Okay.
You, sir.
Ask me questions on that group, right? Then, no. Let's say if you are asking me questions on that group, the group that you created. Let's say create a WhatsApp group for everyone. Okay, what will that group be used for? It will be used for discussions, right?
Yes, sir.
Yeah. So if you ask me, or if anybody asks me questions there, then I would have to answer, right? Does that make sense? So it will occupy.
Sorry, I'm so sorry for that, sir.
I understand your concern, Niveta. It's not that. Okay. I'm saying,
Students can have us class so that we can discuss on.
If you want to interact with each other, yeah, please do that. Okay, if you want to interact with each other, maybe you write. I mean, somebody creates a group and share the link with me. I'll post it in the chat window, and then everybody can join it. But I'm hesitant to join it. I will not be there on that group. That's what I'm saying. Okay, I will avoid it because I've seen that people take advantage of it. Okay, and then they will send me the queries even for very, very trivial details.
Yes, that will not be fine now.
No, okay, but if you want to discuss with other people, I actually encourage it.
Okay, sir. So can I ask Dinesh to take that responsibility, sir?
It's up to you and Dinesh, right?
Yeah, Dinesh, are you here?
I'm here.
Policy. I know that it's against Google's policy. I know that.
Yeah, that's my concern actually. Once we like with the previous mentor, we had the same discussion, but in between of a meeting, one person was intruded and said that it is against to the policy. So that time it felt a little awkward because I've asked the coordinator and I've started to receiving 2 or 3 phone calls stating like this is against the policy. You guys should not do it, or if you guys do it also, like keep it private like that. They said, and there is a lots of
there is a reason for it, right? See, we are freelancers. Do you understand that? There is a difference between freelancing and being a full-time employee at Google.
Yeah.
So we have our own full-time commitments. And if we commit to being a part of the WhatsApp group, and let's say if we are not responding,
it's not that. Actually, in that also, the previous mentor Ashish said like, okay, I'm not going to be a part of it. Like, if you the students want to be a part of it, then you guys can.
But I prefer that. Okay.
Yes, actually, Dinesh, if you can, you create a group and you can share it in the link here in what chat. Those who want to join,
can be a part of that. Okay, there is no harm in that. You should. I mean, I understand from like why. I mean, why Google is thinking like that. I understand from their perspective also, because like if you do that, like, and then it becomes a problem for the mentor, and they are not. So see, some mentors might ask for extra remuneration, right? They don't want to do that. Do you realize it? And it then becomes like a query can come at any time, right? Yes or no?
Yes, sir.
Okay. And then others might get frustrated.
Yeah.
Okay. So it's not a one-to-one job, right? We are not mentoring you one-to-one. It's one-to-many. So only in the class, I think we should discuss the queries. But if you want to go beyond, I would very much encourage that you guys connect with each other. Okay. But don't ask me to be a part of that group. I am a little hesitant towards that. I shared my LinkedIn profile with so many people, and then I got bombarded with so many questions after they graduated. Okay, so it's a strict no-no from my side. But if you want to create a group, well then good. Okay, I don't mind that. Okay, and I appreciate you asking me questions in the session any number of times. and any number of questions, even in the beginning or in the middle, anytime. Okay. So I'll be happy to answer all those questions, but not beyond the session. See, I'm currently taking 15 to 20 extra minutes almost in every session. So I don't mind taking extra time as well, but not beyond that. Not beyond that.
So,
Want me to take extra sessions, 1 or 2 extra sessions, I will take those as well. Okay. But nothing, I would say, beyond the policies of Google. There are reasons for it. Okay, you may be thinking that we have paid, so we should get it, and you do have that service, right? Yes or no? When you are having doubts, you can schedule a one-on-one meeting with.
Yeah.
So you make use of that. I think you are not making use of it because it requires you to write probably or fill a form, right?
But we were probably using it, and the people were so responsive, and they were coming and explaining us, and then they were like in the regional language also. If I'm not comfortable with English, they used to talk with me in Tamil also, and then they were helping me. Yeah,
that is a good thing. So
Yeah.
why don't you make use of that if you have problems? But I understand that you may want sometimes immediate responses, which is not possible with that, right? So you have to wait.
Yeah, but even that also can possible. Like, you know, if some of the mentors from GUI, like I have one person named Surya. He said that if you are raising a query, you can just call me and give me the query number. If I'm free, I'll go ahead and clear you right away. Like that he used to do.
That is good, no? That is good. I mean, if they are providing that service, then make use of it.
Yeah.
I mean, there are ways to overcome the hurdles, right? Okay, but I don't want to be a part of any group. Okay, I'm very sorry for that. Okay, I mean, it's actually beyond what I can do for you.
Okay.
Okay. So I mean, it's something which is not in my contract. Okay. If I were to do this, I would want to be paid more. Okay, which is not the case. Okay. So
Sure.
I mean, obviously, you guys, if you're giving some service to someone, right, you want to get paid. Would you do something for free for your company? No, right?
Yeah.
So that's the same thing here. I'm a freelancer. Okay, I only get paid for the 2 hours. I'm still taking it more. Okay, so think about that. Okay.
Get it.
It's still the 20 minutes of my free service every time. Okay, so I don't mind this though. All right, I'll stop here. We'll meet in the next class, and we will see the implementation of all of these algorithms, and we'll try to do everything in detail.
Okay.
And I'll upload this to your shared drive folder. In the next class, I encourage everyone to bring all your questions. So please go through these topics. You can refer to any material. There are books also shared on your DSM-4 drive folder. Go through it. If you have any questions, then we discuss it in the next session.
Okay.
Here, everyone. Bye-bye.